All right, let's get started. Last time we did see matrix of a linear transformation. So I'll just quickly recap what we were doing. The first result that we saw in the last session was that given two vector spaces, there is a linear isomorphism between them. A linear isomorphism is a linear transformation which is both injective and surjective, or 1, 1 and onto. So when does that happen? There is a linear isomorphism between V and W if and only if, this is a symbol for if and only if, dimension of V is the same as dimension of W. But that this does not say that if the dimension of V is equal to the dimension of W, then every linear transformation between these two has to be a linear isomorphism. That's not the case. For example, you can just have zero map. That is always a linear transformation between two vector spaces. What it says is that there exists a linear isomorphism, or V is isomorphic to W. That is the same thing. And that happens only when there is equality of dimensions. And the other thing that we saw was how to associate a matrix to a linear transformation. So given a linear transformation, P from V to W, where V and W are vector spaces, suppose beta, I just write this out explicitly because at the end of the session it was kind of rushed. Beta and gamma, this is, let's say, W1, Wm, are bases for V and W respectively. Then the matrix of T with respect to the basis beta and gamma. This is one of the ways in which this one of the notations for this matrix. Matrix of T with respect to beta and gamma is obtained using the coefficients of P of Vi with respect to gamma as the ith column. So is this clear? Are these 2 points clear, or should I say a bit more about the second point?
Sir, second point, can you explain?
Yeah. Okay. So if I have a linear transformation and two bases, beta, so both you have a domain and a codomain, which is V and W. They have bases, right? So I'm here assuming that the dimension of V is n and the dimension of W is m. So you have these vectors Vi and Wi, which form bases for V and W respectively. Then you can associate a matrix, which is dependent on the choice of the basis, by the way. And how do I write this matrix? So this would be m of t with respect to the basis beta and gamma is an m cross n matrix. So m being the dimension of the codomain and n being the dimension of the domain. So it's like codomain cross domain, m cross n matrix. And this will have n columns, right? So you'll have columns 1, 2, up to n. And what is the ith column? How do I get the ith column? let's do the first column, for example. You take TV1. What is TV1? TV1 is a vector in W. So TV1, I can write it as summation. I'll just call this A1J WJ, as J goes from 1 to M. Right? So this TV1, I can write it as A1J WJ, and this vector A1J, or A11, A12, so on up to A1N. So this is the coefficient vector for TV1 in terms of WJ, in terms of the basis WJ. So, and this is your column corresponding to TV1, or the first column of the matrix. This is the theoretical explanation. Let's take an example, because that is,
So can I interfere once?
yeah.
Yeah. So just wanted to ask, so in this one, so the matrix is M cross N, right? The dimension of the matrix.
Yes.
This is the
Yes.
transformation matrix, right?
This is the transformation matrix.
Yeah.
Yes.
So in this case, so we are going from Rm to Rm, or the transformation is from Rm
So
to
this is N to M.
N to M. Okay, okay.
Yeah.
From N to N, M, right?
Yeah.
Okay.
Because see, I've said that the basis is V1 up to Vn, so that has to be of the domain. And gamma is the basis of W, which has M elements, so that has to be M dimensional.
Okay, okay.
Right? So you have a vector space of dimension n to a vector space of dimension m, then the matrix will be of order m cross n. So the conclusion after all this will be linear transform. This linear transformation is just like matrix multiplication. So if you want to multiply this with a vector, you will have to have something from an n-dimensional space, right? You have to have something from n cross 1. So that will come from the domain, and that has to be n-dimensional. Even if you don't understand that last statement, it's fine. Just remember that the order is m cross n, which is codomain cross domain. Dimension of codomain cross dimension of domain. Is that all right?
What is codomain?
Codomain is W. Range is the entire, that is what are all the vectors picked up by T. But codomain is there any other terminology that you're familiar with? If a function has a domain and a codomain, right? I don't know if you are familiar with something else for that.
So here
No,
we'll
sir.
have the
Yeah, we are familiar with codomain to domain to
Yeah.
codomain.
Okay. Yeah. Domain is the space from which you get the input, and the output goes to the code.
Sir, what is gamma and beta, sir? Could you? I'm confused. I'm not able to understand.
Beta is just a set of vectors. It's a basis. Beta and gamma are bases. So beta is a basis for V, and gamma is a basis for W.
Okay. Sir.
in this one basically
Maybe
gamma.
let me write it as BV and BW,
So,
emphasizing that this is a basis for V and a basis for W.
so in this one, gamma will be the basis for the codomain, right?
Yes.
And beta will be the basis for the domain.
Yeah. Let me change it from that to this. Is this less confusing? Instead of beta and gamma, if I write script BV, script BW.
So for domain,
basis for V, basis for W.
we can say we are going from BV domain to BW codomain.
Yeah, W is the codomain. And any element of W can be written as a linear combination of elements from BW. Because it's a basis, right?
Sir, what will be the order of the matrix in the codomain? You might have answered it, but maybe I did not catch that. But just
The order of the matrix is dimension of codomain cross dimension of domain.
dimension of codomain cross dimension of domain, which is m cross n. Okay.
Yes.
Sir,
Sir,
in the,
Let's
what?
take
in
an
the
example.
matrix you mentioned, so in the matrix you mentioned that m cross n, but in
Yes.
the like where you mentioned the t cross v cross w, sir. So it's a codomain to domain, sir. There.
See,
The
the
above
domain is
notation
V.
you mentioned that yeah v
See,
to w, right, sir? Yeah.
yes. V is an
So
n-dimensional
here.
space. W is an m-dimensional space. So it's codomain cross domain. The order is codomain cross domain. There's no contradiction. There's no problem.
Okay, please go ahead, sir.
Yeah.
Sir, here
Let's
you wrote TV1 equal to summation of Aij and Wj. Here Wj
yeah.
means it's a TV1 is the multiplication of Aij and
Okay,
Wj.
this is actually T of V1. This is the transformation. I'm see V1 is an element in V, right?
Yeah. Yeah.
It's an element of the basis, but more fundamentally, it's an element of V. So T of V1 will be an element of W. So any element of W can be written uniquely as a linear combination of Wj because Wj's form a basis.
This is okay.
So then you collect all these coefficients in that order. So here, this is important that this is an ordered basis. So the order in which you consider them also matters. So let's take an example and we'll actually see how this changes. X plus y, let's say x minus y.
Before you go to that, what you are basically saying is that the transformation is applied to each basis vector.
Exactly, yeah. You apply the transformation to each basis vector, and whatever outputs that you get, you express them as a linear combination of the given basis for the codomain, which in this case is W, and the basis is given by W1 up to Wn, and you get those coefficients, right? Those coefficient vectors, you put them as columns.
Okay.
Sir, I did not get about the part of Aij and Wj.
Yeah, we'll take this example and probably it will be clear there.
Okay.
Okay. So let me consider the basis B1. I'll just call this B1 now. B1 to be, say, 1, 2 and 2, 1. Is this a basis for R2?
Yes, sir.
Yes.
Right. And then on this side, let me take something like 1, 1, 0, 1, 0, 1, and 0, 1, 1. You can check that this is also a basis for R3. So I have a basis for R2. This is a basis for R2. Ordered basis. I'll just write basis, but the order is important. Basis for R2 or the domain. And this is a basis for R3, which is a codomain. Now I want to compute the matrix of the transformation T using the basis B1 and B2. How would I go about doing that? So first of all, let us see what the order of the matrix is. What is the order of the matrix?
3/2.
Yeah. So it's a 3 cross 2 matrix. And how do I get the columns? Let's say.
Can I ask one? I just wanted one clarification. When we have expressed the transformation in terms of x and y,
Yeah.
there when we are talking about x and y, are we talking about them in terms of the standard basis, that is 1,
Yes,
0,
you can think of it that way. But R2 is just a tuple of the two coordinate, the standard coordinates system.
No, what I mean
R2
is,
and R3.
for example, x plus y, would we say that it is, we are taking the basis 1 and 2, like 1, 2 and 2, 1, and then calculating the x plus y, or we are just taking?
No, even without the suppose you didn't have this thing. if this was not given to you, even then this makes sense, right?
Yeah,
That definition is independent of any basis that you have chosen.
because we are taking 1, 0 and 0, 1, right, as the basis. That's what I was assuming.
No, the transformation just needs to tell you where does each element go. And you know R2 as an ordered tuple xy where x and y are real numbers. On the other hand, you know R3 as the set of all three real numbers, three ordered real numbers, x, y, z, such that x, y, and z are real numbers. So I'm saying that this element of R2, which is x comma y, goes to x plus y, x minus y, 2x plus 3y. This is the function that I'm prescribing, and you can verify that this is a linear transformation without appealing to any basis. I want this basis only when I want to figure out what its matrix is, matrix representation.
Okay.
All right. So, okay. So, in order to get the matrix, I have to compute so I have to compute what is P of V1. In this case, what is V1?
1, 2.
1, 2.
1, 2.
And what is P of 1, 2?
3 minus 1, 8.
No, good. Don't have to worry about that. Now 3 minus 1, 8 is an element of R3. But 3 minus 1, 8, this is not what goes over here. This is not the correct answer. What actually goes here is the coefficients when you express this in terms of the given basis. So this is something times 110 plus something times 101 plus something times 011.
I did not get that.
Okay, maybe we should use this one. Let's just say let's call it ABC. ABC is not used. So since 318, 3 minus 1, 8, any three vector, that is any vector in R3, can be expressed uniquely in terms of any given basis. Is that okay? That is the definition of a basis. A basis is one in which every vector in the space can be expressed uniquely as a linear combination of elements from the basis.
Yes, sir.
So, yeah. So, we know that 11010. Yeah, go ahead.
So TV1 is equal to T1, 2 is equal to 3 minus 1 by 8.
Yeah.
So what is the purpose is to transform from two-sided to three-sided.
Well, the transformation is from R2 to R3. So you input a vector of R2, you'll get a vector of R3.
Okay, then what we have to do?
Now you looked at the first basis vector. So this is what I'm calling V1 and V2. Okay, I'm just using V1 and V2 from the earlier description that I gave you. There's V1 is 1, 2, right? So T of 1, 2, I'll just use this formula to figure out what T of 1, 2 is. And that happens to be 3 minus 1, 8. As you can quickly see, x plus y is 1 plus 2, that is 3. X minus y is 3. 1 minus 2, which is minus 1. And 2x plus 3y is 2 plus 6, which is 8. So I got 3 minus 1, 8 as the image of the first basis vector. But that I have to now express as a linear combination of the basis given on the codomain, which happens to be W1, W2, W3, which is 110, 101, 01. I need to find this ABC such that this happens.
Sir, did you?
Sir, A equal to minus 3, B is equal to 6, and C equal to 2.
Thank you. Minus 3.
6 and 2.
Sir, you are equating it to the 3 minus 1, 8 and getting the ABC values, right?
Yes. That's how
Okay.
these ABC are unknowns, and you'll be solving a system of equations use Gaussian elimination.
Yes, sir. Understood.
And
Sir,
yeah,
a
someone
quick- sir, a
thankfully
quick
did it for
question.
me already.
Yeah, it's a quick question though. The B2, the base that you have defined for the 3 dimension, that one is already given in the question, or you have derived it? W1,
No,
W2,
no, It is given in the question. So I'm saying that find the matrix of the transformation with respect to these bases, these specified bases.
Okay. So on
So,
the new
sir,
basis,
these two bases will be available in the question. It will be given
Yes.
B1 and B2.
Yeah, if you have to find the matrix of the transformation with respect to some basis, the basis will be given.
Okay, sir.
So, sir, now the transformation vector will be the coefficients, right? The -3, 6, and 2.
Yes. So this will be your first column.
Okay.
And then the second vector. Now I look at, for the second column, I look at the second vector, I look at its image, and that happens to be 3, 1, and 4 plus 3 is 7. And this also I have to express in terms of, let me call this like A prime because I don't want to use the same symbol. A prime, B prime, C prime. And does anyone already have the solution for this as well?
sir, again a quick question though. Transformation of V2, is that again given that the transformation of V2 is 317 that you are writing?
It's computed.
The formula is given, right?
Oh, you're computing. Okay. Sorry.
Sir, I got understood, but the part is that -3, 6, and 2 computation, how?
So this, did you understand until this step?
Yes, sir, I
I
understood
want to
very
find
clearly.
A, B, and C such that this has to happen. So before you get to this thing, there is an intermediate step. Someone gave me the solution, so I just used it. But what you have to do is you have to just write this as so. Okay, wait. This is just solving a system of equations, right? So what do you have to do over here? This I can write as A plus B, A plus C, and B plus C. Is it not? So I need to solve this system of equations for A, B, C, where A plus B is equal to 3, A plus C is equal to -1, and B plus C is equal to 8.
So the value of A dash, B dash, and C dash.
Yeah.
A dash is -1.5.
This is fractional. Okay.
B dash is 4.5. And
Yeah,
C dash is
that's
2.5.
next.
8 by 2, 9 by 2.
So this was 1.5. This was 4.5.
Yes. And last one was 2.5.
2.5. Once again, to find these exact values, you have to solve this system of equations for A prime, B prime, C prime. Someone has already done that for me, so I'll just use it.
Sir, I don't know, somebody has learned before, but I am not able to get A plus B, A plus C, and B plus C.
Did you not understand how this came about? Or
Yes, I understood that, but -3. Please, can you calculate -3 first so that I can get? क्योंकि अगर मेरा बेस ही सही होगा तो फिर आएगा ही नहीं कुछ समझ.
Okay. See, this is something that has already been covered, but I'll go through it quickly once again. So you want A, B, and C such that this has to work, right? I want to find A, B, C such that this happens. So I want A plus B is equal to 3, B plus C, or let me write A plus C is equal to -1, and B plus C is equal to 8. You do it in whichever way you want. Suppose you subtract these two, you will get B minus C is equal to 4. So B minus C is 4 and B plus C is 8. Gives me B is equal to 6 and B is equal to 6 and C is equal to 2. This gives me B is equal to 6, C is equal to 2, and A is equal to whatever is remaining.
-3.
Next. So this is just solving a system of equations which is covered in week 1 to 4. So this is why I didn't go go doing it, because if I keep doing the same things from previous week, then we'll not be able to cover the content. Is this clear now? At least this part is okay now?
Yes, sir.
Yeah. Most of the time, what happens in linear algebra is you have to solve a system of linear equations. So things are expressed as linear combinations of some things, and you want those coefficients, you solve a system of linear equations. You translate some question into the language of matrices or coordinate vectors, and then solve a system of linear equations. So that is why the course is structured in such a way that you learn how to solve systems of linear equations first in the first 4 weeks, and then go into linear algebra where you see sort of an application of that, which is what we are doing right now. And then you will see calculus where a little bit more of linear algebra is used. So, okay, all right. That's enough about this, but at least did you understand how to get the matrix of any transformation given any two bases for the domain and codomain?
Yes, sir. It's clear.
Yeah. So the conclusion is that after you assume basis for the domain and codomain, linear transformations and matrices are sort of interchangeable. Given a linear transformation, I can get a matrix. And given a matrix, I can get a linear transformation. How do I do that? It's just, if you have a matrix, then matrix multiplication is a linear transformation. So these two are in one-to-one correspondence with each other. Not a major point, but just something to remember. And now we go back to linear isomorphisms.
Oh, sir.
Yeah.
So we have got two set of values for A, B, and C. Now, what is the next step, sir?
So you got this A, B, C, and A prime, B prime, C prime, right?
Yes, sir.
A, B, C, the coefficients in order of the first image of the first basis vector is the first column. That's what we did over here.
Yes,
3
sir.
3,
After
6, 2.
getting this matrix, how can we verify whether this works or not? That's what my question is.
We have to multiply it with something.
I'm not getting the correct answer. That's why I'm asking. I'm getting a matrix as minus 6, 15, and 7. When I try to transform 1, 2.
Okay, so what happens is once you have the matrix of T with respect to, this is beta 1, beta 2, then if you multiply any vector, and by a vector I don't just mean the vector as it is. Let me tell you what all that is. Before this, we probably need that one. So this is the equation that you can use to verify. Now, what does this equation mean? You know what this object is, but what is this object and what is this object? V is any given vector in your domain, and V beta 1 is the set of coefficients of that vector, and TV beta 2 is the coefficients of TV in the basis beta 2. So, for example, let us see what, give me any arbitrary vector in this thing. So let us take 1, 2 itself. So 1, 2 belongs to R2. Now what is 1, 2 beta 1? So what is the coefficient vector of 1, 2?
1, 1.
This is 1, 0. No? Because what is the coefficient vector of this? Meaning, you look at this vector and try to write it as a linear combination of the given basis. Something times here plus something times here. Your given basis, this beta 1.
Got it, sir. Got it.
The given basis beta 1 is 1, 2, 2, 1. So 1, 2 can be expressed uniquely. This is the only solution in which you can express 1, 2 as a linear combination of 1, 2 and 2, 1. The coefficient is actually 1, 0. The coefficient vector for 1, 2 is 1, 0. So now let us take this matrix. What was it? Minus 3, 6, 2 was it? Minus 3, 6, 2 and minus 1.5, 4.5, 2.5. Minus 1.5, 4.5, 2.5. Now if I multiply this with 1, 0, what will I get? What should I get?
The first column itself.
Minus 362.
Minus 362.
So,
Now what this says is that minus 362 is actually the coefficient of
the
T of
linear
V.
combination of beta 2.
So yeah, so if I take minus 3 times, what was it? 110101? Yeah, that was the order, right? So if I do, so what is the vector for which this is the coordinate vector? Minus 360. It is 3 times this plus 6 times 101 plus 2 times 011. And what does this turn out to be?
eight. Last one is 8. 3.
3
minus
minus 1,
1,
8.
8.
And what is P of 1, 2?
Your 1, 2 is.
It has to be this. We did verify over here that
3
P of
minus 1, 8.
1,
3
2.
minus 1, 8. 3 minus
Yeah.
1.
Right. So this P of 1, 2, the coordinate vector of T of 1, 2 in beta 2 is the same as matrix of T in beta 1, beta 2 times the coefficient vector of 1, 2 in the basis beta 1.
Okay. So basically the other, for the other, other vector, so T2, 1, beta 2, say for example, it will be basically MT beta 1 to beta 2 into 2, 1, beta 1, right?
2, 1, beta 1. But what is 2, 1, beta 1? What is the coefficient vector of 2, 1? 2, 1 is already a basis vector, right?
Yes. It will be 0, 1, I think.
Yes, it is 0, 1.
0,
It is 0 times 1, 2 plus 1 times 2, 1, right?
Yeah, because it is ordered. No?
Yeah, it's ordered. So it will be 0, 1. So when you
Yes.
multiply this matrix with 0, 1 instead of 1, 0, you'll get the second column. And the second column is minus 1.5, 4.5, 2.5. And here you already know that that is actually the coordinate vector of V2. So it is T of V2 beta 2. I'm going a little fast over here, but I have to because this is something that you can verify with problems later. So the point is, once you get the matrix of a transformation with respect to any given basis, this is just matrix multiplication in the sense that if you take the matrix and multiply the coefficient vector of any vector on the domain, you will get the coefficient vector of the image. Is that okay? So let me just write that down. Multiplying the matrix. I'm not going to keep writing matrix with respect to basis beta 1, beta 2. All of that is understood. Multiplying the matrix with the coefficient vector. So what do I mean by coefficient vector? That is the coefficients which are obtained by expressing it as a linear combination of the given basis. With the coefficient vector, multiplying the matrix with the coefficient vector gives the coefficient vector of the image. I would not like to spend more time on this because there's a few topics more to cover. Maybe we'll come back to it with an example, another example at the end, if there is still confusion. So, yeah, going back to linear isomorphisms and all that. Let's just break it over here and then say, going back to injectivity and surjectivity. So for isomorphism, two things that you have to check are injectivity and surjectivity, right? Can someone recall what is injectivity?
1 1. We check for zeros, sir.
It's one-to-one relation.
Yes. Yeah, what is the mathematical formulation of that? Suppose P is injective. P is a map from V to W.
T of
Now,
0.
when do I think? Please repeat.
If we take 0, basically T of 0 will be the 0.
Of W.
Yeah.
T of 0 is always the 0. That is not when it is injected. T of 0 is always 0.
No other vector should be 0, sir. Like,
Exactly.
There
So
should be only
T
one
of 0.
vector codomain.
Yeah. So T of V is 0 implies V is 0. And surjectivity demands that for all W in W, there exists a V in V such that, can you complete this sentence?
T of V is equal to W.
Yeah. So this condition actually is only in the case of linear transformations, the first condition for injectivity. Surjectivity is, so in general, injectivity, you would have to verify that no two elements go to the same element, or T of V1 is equal to T of V2 implies V1 is equal to V2. This is the most general formulation of injectivity. But in the case of linear transformations, we just need to check that the pre-images of 0 is just the singleton 0. So let us just write one. Very simple examples of these things. So injectivity. So xy goes to, let me say, x and the same thing as last time, 2x plus 3y. Let's just take that itself. Now, if I want to check if it is injective, what do I need to do? Is this map injective or not? Or at least guess. Is this map injective or not?
So it is injective.
Why is it injective?
Because for x and y equal to 0 only, it will give 0.
Exactly. So if I have x plus y, x minus y, 2x plus 3y, this is equal to 0, 0, 0. In particular, you should have x plus y is equal to 0 and x minus y is equal to 0. And when does x plus y equal to 0 and x minus y equal to 0 happen? It is only if x is equal to y is equal to 0. So the only pre-image of the 0 vector in the codomain is the 0 vector in the domain. So this is injective. So let's take an example of something that is not injective. Say x plus y x plus y. So I have already said that this is not injective. Can someone give me an argument for why this is not injective?
X not equal to Y.
So for there would be many values basically.
Give me at least one.
X is equal to minus y, sir.
X is equal to minus 1. And
Sir, x is equal to minus y for
okay.
all x and y.
Minus
So
right.
one particular value.
-1,
1 minus 1.
-1, yeah.
Yeah. So this goes to 0.
0, 0.
Even 2 minus 2 will go
So-
to 0. Yeah.
Yeah.
Even 0,
So-
0 goes to 0, so both are
Yeah.
there, so it should not be 1, 1.
Yeah. I just need to check that as long as the pre-image of 0 is not a singleton set, then I'm good. So let me just write this. So I'll call this transformation T again. What is this curve T? I'll define next. But consider this set x comma minus x, x in R. Any element of this set is mapped to 0, 0, right?
Yes.
And
Yes,
this is
sir.
precisely the entire set. There's no other element which is mapped to 0, 0. Because well, if something is mapped to 0, 0, then x plus y is equal to 0, then y is equal to minus x. So the point has to be of the form x comma minus x. And note
So-
that this is a subspace, right? This is a subspace. This is a span of what vector?
X.
This is just span of the singleton 1 minus 1, because everything is of the form x times 1 minus 1. So this is exactly span of 1 comma minus 1. This is a subspace. So that's one. So let's look at a surjective map. This is from R2 to R. Okay. So is this surjective? These are alternative names. But yeah, tell me if this is surjective.
Unique values.
So
Oh yes, sir, it is surjective.
So given any real number, let me call it x naught. What is the vector in the domain which is mapped to x naught?
x naught comma y. Oh, sorry.
X naught comma any value of y will do.
Anyway.
X naught comma 1.
Is x naught comma y mapped to x naught?
Oh, sorry.
X naught by 2.
X naught by 2. Sorry.
X naught by 2.
Yeah. So let's just take it to be 0 to just drive home the point that all I need is one p. So in this case, every time I'll just write t. Okay, t is assume that the transformation is going by t. So the image of t is something that you've already seen in Math 1 and here, right? So what is image of t? Image of t is exactly R. Any real number can be realized as the image of something. So it's not y. So let's give an example of something that is not surjective. Let me just put xy in xy0. This is a map from R2 to R3. And can you give me an element of R3 which is not the image of any element of R2?
X comma y comma any value. Let's say 1. X comma y comma 1.
Yeah, when I'm asking for a specific value, you can just give me something like this. 1, 1, 1. Is there any element such that that element is mapped to 1, 1, 1?
No.
No.
So there does not exist. So this does not happen.
Sir, this is given because xy only defines for xy0, right?
Yeah, the definition of my transformation is that xy goes to xy0. So the third coordinate will always be 0, irrespective of what I start out with. But even if I take something like, let's say, xy, x plus y, even then, okay, let's, instead of doing the easier xy0, let's do xy, x plus y. Even then, 1, 1, 1 will not be picked up. Because if 1, 1, 1 was the image of some xy, then x has to be 1, y has to be 1, and x plus y also has to be 1. Even that is not going to happen, right?
Yes, sir.
Sir, ये जो the kernel that is given in the not injective part is a like domain, na?
Kernel is a subspace of the domain, and that is not the entire domain, right? The entire domain is R2.
Entire domain is R2, but representation of KERT.
Yeah, I've just written it down. I'll explain what kernel is, and then it will be clear. Here I'm just hinting at what is to come in the next half.
Sir, is it safe to say that if there's more than one kernel in that example that you've given, the second column, there's more than one kernel, basically it's not injective, right?
See, kernel is the pre-image of the zero set. Sorry, the zero vector.
Right.
And that will always contain the zero vector of the domain. That is by definition of a linear transformation. If it contains even one more element, then by definition it is not injective. So kernel being singleton or not singleton implies whether the is equivalent to saying whether the transformation is injective or not injective.
Okay.
All right. So back to not surjective thing. 1, 1, 1 is not picked up because x equal, there is, you can verify that there is no xy which is mapped to 1, 1, 1. In this case, what is the image of T? Can anyone give me the description of all possible vectors which are picked up? It is simply x, y, x plus y.
1 plus x plus x.
Where x and y. So this is just the definition. It's getting small and maybe difficult to read. Okay. But can you tell me what this is the span of? This is actually a subspace, and it is the span of two vectors.
1, 0, 1 and 0, 1.
1 1.
This you can verify. If you don't see it immediately, you can verify that this is happening because x y x plus y can be written as x times 101 plus y times 011. So this is the span. So in all these cases, so okay, let me just write this over here also. The pre-image of this, which I'll call T, in this case it is just 0, 0. So when you are studying or analyzing injectivity and surjectivity, there seem to be two important players called these kernel and image. Kernel is related to the injectivity and image is related to the surjectivity. Image is something that you are familiar with. Kernel is something that is specific to linear structures. So kernel of linear transformation denoted ker of T. This is the set of all vectors in the domain. Always assume that T is a linear transformation from a vector space V to W. I'll not keep writing that. Such that T of V is equal to 0. So what is it? It is exactly the pre-images of 0. What are all the elements that are mapped to 0? This I'll call the kernel of T. This is just and using the kernel, I can just reformulate the definition of injectivity as T is injective if and only if kernel of T is 0. So what is 0? This 0 is the 0 vector in V. We just write it as 0. All right. So is this statement clear? So if you're okay with this statement, you should be okay with this statement also, right? Injectivity is that pre-image of 0 is just the 0 element, and the pre-image of 0 is what I'm calling the kernel. So injectivity is equivalent to saying that the kernel is the single element set 0. Is that fine?
Yes, sir. So if it is not singleton set, then it's not injective.
Yes. In fact, it cannot have, let's say, 2 elements, 3 elements. It cannot have that. It is either singleton or it will be infinitely many, because it's a subspace.
Can we have one example?
So this is why I gave you the examples beforehand itself. I can give you another example if you want. So in this case, you see x comma minus x as x varies in R. So you have infinitely many, as many real numbers as you have that many elements in the kernel. And if you want a proof of why the kernel is a subspace, you can easily see that if v and w are in the kernel, then t of v plus w, this is what t of v plus t of w, because of linear transformation properties, which is 0 plus 0, which is 0. What does this mean? V plus w is also in the kernel. So if v and w are in the kernel, then so is v plus w. Similarly, t of cv, once again by linear transformation property, is c of tv. tv is 0 because v is in the kernel. So this is 0. And this implies that cv is also in the kernel of t. So sums and scalar multiples of elements in the kernel are in the kernel. So kernel is a subspace, and a subspace has either one element, that is the trivial subspace, or it has infinitely many elements. Like if it is one dimension, it's like a line. If it's two dimensions, it's a plane, and higher dimensional subspaces and so on. So yeah, if you have a doubt, you can just speak up. You don't need to raise your hand. I might not always look at it.
Okay. Sir, I have a question though. When you wrote that kernel of t is equal to 0 inside the curly braces,
Yeah.
did it read that it's one element, like one vector, which essentially translates to the 0 vector? Does it read like that?
Yeah. So if you have one element set, you will write it as this, right?
Correct.
So that V0 is actually 0 because 0 is always there. 0 should always be there.
Okay, V naught is always there. Okay. Okay. Oh, that's why, because V naught will always be a 0 vector, is why you have written it as a 0 in
See,
there.
kernel T cannot be empty. Kernel T
That is
has to
correct.
contain at least 0. By the definition of a linear transformation, P of
Correct.
0 is 0. So 0 is always contained in the kernel. So if nothing else is contained, it is the single element set in which that single element is actually 0.
Okay. But there can be, like in another basis, there can be like just one vector which is not essentially 0 0 or 0 0 0, whatever it is, that can
So
map.
irrespective of what basis you take,
Uh-huh.
the 0 element has to go to the 0 element. The 0 vector has to go to the 0 vector.
That is correct. That
Because
is correct. It has to
because
go
what is the coordinate representation of the 0 vector? It is just 0 0 0,
0 0. Yes.
irrespective of what basis you take.
Uh-huh. Okay. 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 Got it. Got it.
Sir,
Got
in
it.
this, since you have written like V and W belongs to the kernel T, or T
Yeah.
V equals W equals 0. So that means in this case also V and W is 0 only, right?
No. This is a separate statement. This is a statement, or this is the proof why kernel T is a subspace.
Okay.
Yeah.
In general, kernel T need not be just the zero set. No, it could have other vectors as well. But whatever vectors it has, if it has two vectors, then the sums of those vectors are also in the kernel. If it has a vector, the scales of that vector is also in the kernel. So it's a subspace. So how do you check whether something is a subspace? You take two elements from that space and see if the sum of those two vectors are in that space. You take any arbitrary element from the space, then you see if every scale of that is in the space.
Got it. Can you scroll up, please? I have a question related to this only. Okay, so here the fourth one where you said that it's not surjective. Okay, here you
Yes.
don't have a kernel, is it?
No, we are talking about when you're talking about injectivity, kernel comes into picture. When you're talking about surjectivity, the image comes.
Okay, but then I'm not understanding that statement. Then where is that V and W coming from? I mean, if the injectivity is the question, then there will be one-to-one mapping, which means that one vector in one
Yeah,
vector
yeah.
space
So
map to zero
kernel
vector.
of T is used to give a condition for injectivity.
Correct.
But in general, kernel of T need not be zero.
What is general kernel of T?
Like given any transformation, take for example this transformation, even that
Uh-huh.
has a kernel. The not injective example also has a kernel. In this case, the kernel is exactly x comma minus x, which is the span of 1 comma minus 1. It has infinitely many vectors.
Oh, okay. So, okay. Now I get it. Okay, so I can take this example, x comma minus x. Okay, thank you.
Set of all
Yeah.
vectors mapping to 0.
So
Okay.
if you're asked, kernel T is the set, let's say 1 comma x x in R. So usual R2 this cannot happen. For example, is not possible. Assuming usual operations, of course, there are vector space structures where this can have zero and all that. Why? Because this does not have 0, 0, and this is not a linear subspace of R2, of the usual R2. Maybe there should have been some spaces between these sentences. So, yeah. Do you understand this sentence?
Yes, sir.
Yes, understood.
So does it mean that any linear combination of all such vectors is not going to give us 0, 0,
Of what vectors?
1 comma x?
1 comma x cannot be the kernel because it doesn't contain 0, 0 in the first place, right?
Yes.
So
So
if the
that,
first place is 0, then it will be a kernel.
it could be a kernel of some transformation. Take, for example, x comma y goes to x.
The similar part. If I say 1 comma 0 is also a kernel.
Just 1 comma
Uh,
0? 1 comma
Yes,
0
yes.
doesn't have, it has only a single element. No, so that's not the 0 vector. So 0 vector should always be there. So if you want something like this, maybe
This can be a
that
kernel, right?
1 plus, this can
Yeah.
be a kernel because that's just, yeah.
So in short, we can say the first x position should be 0.
Not necessary, as in you could have something like x comma x. This is also fine because so things like this should not happen. Say x comma x plus 1 cannot happen because then again 0, 0 is not there. Or if you take say x comma x square, this cannot happen because even though 0, 0 is there in this set, this is not a linear subspace.
Linear, that's not linear.
This is
x
something
comma
like
x
this.
square, x comma x square is a can be a kernel, na?
It cannot be a kernel. It's not a linear subspace. So take for example 1 comma 1 belongs to this set. Let me call this set W. Okay, 1 comma 1 belongs to W, but 2 comma 2 does not belong to W. So this is not a linear subspace. Kernel needs to be a linear subspace.
Sir, if there is a transformation, like if we define a transformation where 1 comma 0 is transformed into 0 comma 0, then kernel of T is possibly, is it possible, sir?
Let's take that example. You are saying that 1 comma 0 goes to 0 comma 0.
Yes, sir.
And what about, you are not going to specify what happens to any other basis vector?
No, sir. I'm not specifying.
Okay. So then what are all the transformations with this property? So in this case, you can say that suppose under T 1, 0 goes to 0, 0. So you are working with the map from R2 to R2, correct?
Yes, sir.
So then you can say that x, 0, x in R, this set is contained in the kernel. Because you have not specified what happens to the other vector, right? So suppose 0, 1 also goes to 0, 0. In that case, what is your transformation? Your transformation itself is the zero transformation. Like every vector goes to 0. Everything collapses. Everything is the kernel.
So in this case also, the first case also, everything is collapsed into 0, right? 1, 0 to
So
0.
when you just 1, 0 goes to 0, 0, it just says that the vectors in this line 1, 0 is what?
X-axis.
X-axis, right? So the things on the red line, these guys collapse to 0. But not necessarily the y-axis. We have not said anything about the y-axis. You can have, say, 0, 1 goes to 0, 1.
Okay. Correct. Got it.
So if you want a more explicit example, let's say x, y goes to 0, 1. So this does satisfy the property that 1, 0 goes to 0, 0. But this is not the zero map. So this map could be the zero map, or it could be a non-trivial map also. So, but what you can guarantee is that this set x, 0 is in the kernel. Why can you guarantee that? Since 1, 0 is in the kernel, any scale of 1, 0 is also in the kernel. And what is any scale of 1, 0? It's just the entire x-axis. Is that clear? Does that answer the questions that you had?
Sir, could you once again explain the last two lines?
Okay. So the only condition that you want is t of 1, 0 is 0, 0. So what happens to t of x, 0? This is t of x times 1, 0. This is by linear property. It is x times t of 1, 0, which is x times 0, 0.
Yes, sir.
Which is 0. So x, 0 belongs to the kernel. This much you can guarantee. So the entire x-axis is a part of the kernel, is a subset of the kernel. But the kernel itself could be the entire. The kernel could be the whole space itself. If you consider the map xy goes to 0, 0 for all xy, which means that every vector is mapped to 0. This is a trivial transformation. Essentially, everything is collapsing. So it's not even transforming anything, but it is still a linear transformation by definition. Trivial linear transformation. This does satisfy your condition that 1, 0 goes to 0, 0. But in this case, the kernel is R2 itself. So kernel of T could be R2 or just the x-axis. There are examples for both. Is that fine?
Yes, sir. So what would be the kernel, full kernel, sir? Like, can we define
without specifying what the map is? Like you have not specified the entire. You have specified the map. You have just said that the image of one vector is no. Then
Okay.
only this is what you can. This is the extent of what you can deduce about the kernel.
Okay. If the other one is also like this, like 0, 1 is also from 0, 0, then it will form a zero transformation, and the kernel of 0 would be?
Yes. If 1, 0 goes to 0, 0, and 0, 1 also goes to 0, 0, then x, y will go to 0, 0, right? Because x, y is x times 1, 0 plus y times 0, 1. So
Yes,
you
sir.
use the linearity properties. It becomes x times t of 0, 1. Sorry, x times t of 1, 0 plus y times t of 0, 1, which is x times 0, 0 plus y times 0, 0, which is 0, 0. I'm just saying all of this without writing it. I hope.
Yes, sir. I'm able to understand, sir.
Yeah. So in that case, it becomes a zero transformation. In that case, T is just the zero map. So if everything goes to zero, the kernel is the whole domain, right?
Okay. If it is 0, 1 belongs to 1, 1.
If 0, 1 goes to anything non-zero,
Yes, sir.
then kernel of T will be equal to the x-axis.
Okay. The big it won't be a subset, it will be the set, right? That's what.
Yeah, it will be equality. Yeah.
Okay. Yeah, got it, sir.
So yeah, maybe you can actually give a more refined answer than just this statement that the kernel of T is the whole space if 0, 1 is mapped to 0, 0, and the kernel of T is equal to the x-axis if 0, 1 is mapped to something non-zero. Yeah, you can verify that later. So, okay, this is about the kernel. And the other important subspace. So, what is kernel T a subspace of? So, this is subspace of what? Is a subspace of?
R, sir.
Well, in general, of the domain. It is V.
Yeah.
So, next you have image of a transformation. Denoted Im of T. This is the set of vectors in the codomain. Once again, I'll remind you that we are working with transformation from V to W such that W is equal to T of V for some V. This is just the image as a function. There is no linearity property yet that we are talking about. So you look at all possible vectors and their images and you collect all possible images. That is your image set. Now, once again, okay, the condition for surjectivity is, can someone guess or give the condition for surjectivity in terms of image? This is just something from function. It is a language of functions. There's no linearity. When do you say that something is surjective or onto?
Range and codomain are same.
Yeah.
Yes,
So
when
this is actually the range. Image of T is just the range, right? And the codomain is this. Yeah, range is another name for image. So if image is equal to the whole space, then it is surjective. And if kernel is equal to the trivial space, then it is injective. So, and even this happens to be a subspace. Image of T is a subspace. But this time, this is a subspace of what? It has to be of W because you are looking at elements from W, which are images of some vectors in V. So I'm not going to give the argument for it. You can figure it out quite easily. You can take two elements in the image and look at their pre-images, and then you can add those pre-images to get a pre-image for the sum. So the sum is also in the image. And similarly, you can just scale the pre-image to get a pre-image for the scale. So the important point is to note that image of T is a subspace. The proof is not as important in the context of the proof. So yeah, similarly you can say
image of T, one example, please.
okay, once again I'll cheat and I'll say that here we have already seen two examples. One in which the image is the whole space. So in this case, you saw that the image is R. In this case, you saw that image is not R3. You can have elements of R3 for which the image is not the whole codomain. Right? And in both cases, we also readily see that these are subspaces. So I'll come with more examples a bit later. Once I finish the concepts, I'll take some problems as well. But the condition for surjectivity is in terms of the image, and it's a subspace. So to summarize this page, it is that given a linear transformation, there are two associated subspaces, and this has nothing to do with choice of basis or anything like that. These subspaces are defined independent of basis. Given a linear transformation, I have a subspace of the domain called the kernel, which can be used to detect whether the transformation is injective or not. And I have another subspace of the codomain, which can be used to detect whether it is surjective or not. So these two subspaces play an important role in understanding the transform.
Can you repeat, sir, once more?
Okay, so let me write that. Given a linear transformation, P from U to W, there are two subspaces. Kernel of T, which is the preimage of 0, this is a subspace of V, and image of P, this is a subspace of W. Which can be used to determine injectivity and surjectivity of P respectively. Kernel of T being 0 is equivalent to injectivity. Image of T being equal to W is equivalent to surjectivity. Right?
Sir, one doubt, sir.
Yeah.
Sir, in W, we can have two vectors from the domain which can have an image in W. So then image of T will consist of both.
I didn't get what you were saying. Sorry.
So from the domain, we have two vectors such that they
Okay.
both are having the same image in W.
All right.
So the image of T will contain both V1 and V2.
Now, image of T contains vectors from W. So T of
Oh, okay,
V1
okay,
and
okay.
T
So
of
it's just the
T
image
of
part,
V1, T
not
of
the
W.
original vectors.
Yeah, it's not the original vectors, right? It's
Okay,
that's why I was stressing that it is a subspace of the codomain.
okay, sir. Okay, got it.
So even if multiple guys map to the same vector, that vector is just picked up in the image. That's all. It does not have a reference to where it came from.
Okay, sir.
Whether it is the image of something or not, that is all I'm worried about. Say, take for example this example 3, surjective example over here. If xy goes to 2x, you know that 2 comma 0 goes to or yeah, not 2 comma 0. Let's say 1 comma 0. 1 comma 0 goes to 2. 1 comma 1 also goes to 2. Or anything, I mean, 1 comma anything goes to 2.
Yes, yes.
2 is in the image, and that does not depend on whether or not multiple guys go to the same thing.
Correct, sir. Correct. Got it.
Yeah. So
it says like we are having x comma y as 2x, so they are like it's not that x is belonging to a particular thing.
yeah. So I'm just looking at what are all the images. That's all. X
So
comma
we can
y
say a
could
set has an image. A set has an image, a particular set.
present as an image here. We are looking here at the image of the whole domain. You can restrict the function the transformation to specific sets and talk about image of those sets also, but that is not considered over here. Yeah, so for any element of the codomain to qualify to be in the image, what we require is that there is at least one prime. Is that okay? Shall I go ahead?
Yes, sir. Yes, sir.
Yeah. Now, once we have any concept for linear transformations, it is now important to ask what does it mean for the matrix of the transformation. So when we were discussing matrix of the transformation, we said that a transformation is essentially, I erased that and didn't write it again, but linear transformations are in one-to-one correspondence with matrices. So whatever you learn about matrix transformation, a good question to now ask is what does it mean? What is the corresponding statement in the language of the matrix of the transformation? So let us see what kernel and image are in terms of the matrix. I'm just going to give the statement. I'm not going to give the proof. So suppose I won't write out everything. You have T weak to W, a linear transformation, and I'll just call it B1, B2. B1, B2 are bases for V and W, respectively. Then kernel of T consists of vectors whose coordinates or coefficients is what is this coefficient? This coefficient vectors lie in the null space of M of P, beta 1, beta 2, or P1, P2. What it is saying is that kernel of T, the set of vectors which map to 0. This is the same as the null space of the matrix of the transformation.
So it will be represented as 0, 0, 0, 0.
What will be represented as 0, 0?
Kernel of T.
Kernel of T consists of all vectors, right? It could be like 0, 0, 0 will always be there. It could have more things as well. It could have non-zero vectors as well. I'm not talking about injective linear transformations, right? So if it's an injective linear transformation, then sure, the only vector that will be in the kernel is 0, 0. But in what this statement is saying is that in terms of the matrix language, if I look at the matrix, so of course, when I give an example, this will be more clear. But for now, just understand that if I'm given a matrix, I can compute its null space. What is the null space of a matrix? If you remember from week
Solution
1 to
space
4.
are all values of x's.
Yes, all vectors x, such that ax equal to 0. In
Yes,
this case, that a being m of t beta 1, beta 2, b1, b2. So computing the kernel, if you want to compute the kernel of a transformation, you just need to look at the null space of its matrix. You will get a vector in the null space, but that vector is not actually the vector in the kernel. That is the coordinate vector of the kernel. So this is a little bit confusing until you solve a few problems. So you have to do that by yourself. But here, let me give you an example.
So basically, that null space of the matrix are the coefficient vectors, right?
null space of the matrix is the coefficient vectors of the vectors in the kernel. Yes.
Okay. All vectors in the kernel, correct.
Yeah. And that is actually believable, right? Because what is kernel? Kernel is vectors which go to 0. And what is null space? Null space is something like this times, say, this vector is, say, v prime. It becomes matrix multiplication. And if t of v is equal to 0, then this one will be 0. By definition, t of v is equal to this matrix multiplication. The coordinates of t of v is equal to this. And that means that v beta 1 is in the null space of matrix of.
What is V beta 1?
V beta 1 is the coefficient vector of v. So this is what we had discussed earlier over here. That yeah. So this part.
So this v is also the coefficient vector, right, of the basis b1.
So v is a vector. V beta 1 meaning coefficient vector of v in the basis beta 1.
Yeah.
So if TV is equal to 0, then TV beta 2 is always 0 because the coefficients of the 0 vector are always 0.
Right.
So it implies that matrix times this coefficient vector is 0, which means the coefficient vector is in the kernel or in the null space, sorry, of the matrix of the transformation. And you know how to compute the null space of a matrix. How do you do that? So let's take the earlier example. I'll just write earlier example. The matrix of the transformation with respect to whatever basis was given at that time. I'm not going to specify that. It was something like -3, 6, 2, and -1.5, 4.5, 2.5. Was it? No, the last. Yeah, it is 2.5. So this was what we obtained as the matrix of this transformation with respect to some basis. Now, if I want to see what the nullity of this or what the null space of this is, what do I do?
Row reduction.
Row operation. Row reduction.
Yeah.
Gaussian elimination.
Yeah. So I divide the first row by -3 to get
Yes.
something like half, and then 6,
Yes, sir.
4.5, 5. Sorry, this is not equal. This transforming. So row operations will give me 0.5 and 0. What is it? 1.5.
1.5. Yes, sir.
Thank you. And then the last one is I'll just remove this as well, and this is also 1. So this will be 5. I can make it RREF also. 0, 0. And I can just do this. I make it this. I've skipped a few steps because RREF is something I expect you to be familiar with. But this is the matrix that we get. This is the reduction of M of t. So what is the null space of M of t?
1.
0, 0, 1. Oh, sorry, 0, 0. My mistake.
Nullity is 1.
Nullity is 0, no?
Nullity is 0.
The null space of this is just 0, 0.
Okay.
Why? Because if I multiply this with x comma y, I need x to be 0, y to be 0.
Yeah, x equal to 0, y equal to 0.
Sir, similar thing. If 1 0 0 1. If we have 0 0 niche, then then null
Could you
space will
repeat the
be
matrix? Okay, we'll
for
take up an example where the null space is actually non-trivial. In this case, the null space is trivial. Null space of the matrix is trivial, which means that kernel of T is also trivial.
Sir, my question is something else. I said the last augmented matrix, reduced matrix, if we
Yeah.
say 1 0 0 1 0 0 0 0, then null space will be two sets of 0 0 0 0.
If you have a 4 cross 2 matrix, 2 matrix is what you're asking.
Yeah. Then what is the null space then?
It
Even
is
then,
0,
it is
0.
just 0 0, right? Because these things don't contribute, however many there are, because you'll be multiplying it with a 2 cross 1 vector,
X
say
and
x
Y.
comma y. So the first matrix multiplication, first row will give you x is equal to 0, the second row will give you y is equal to 0, and everything else is irrelevant. Is that clear?
Null space will be remaining same.
Yes, but that will be a different system, right? That will be a different transformation. That will be a transformation
Sir,
from.
what if for 1 0 0 0 0 0? Like I'm changing the second column 1 as 0.
Yeah,
Yeah,
then
yeah,
you'll
yeah.
have some null space, right? You'll have
I
some,
guess
if it is something like
his
this.
question is this one.
Okay, okay.
Yes,
In this
yes,
case,
yes.
yeah. So if you have, what is the null space of a matrix whose RREF is this? It is x is equal to 0 only.
Y
Yes.
can take
So
and leave away.
how will you determine how many linearly independent elements are there
Only
in
one
your null
linearly
space?
One
independent
linear
pivot.
It is the number of independent variables,
Yeah.
right, or non-pivot variables. So in
So,
this
so
case,
the
there is
nullity
one
will be 1
non-pivot
here.
variable. Nullity will
What
be
will be the
1.
null?
This will be the null space.
Yes, correct.
Why? Because the second column is a independent variable column.
Yes, sir. Nullity equal to number of free variables.
Please explain.
I think this is week 2 content. Is it okay if I take it at the end?
Sir, 0 comma y, just a simple bit, a simple clue.
Okay, so if you want to calculate the null space of this, you would do this, correct? You would want to solve for all possible xy which satisfy this. But what is this? This is x 0. This would be 0 0 0 over here. This has to be x 0 0 is 0 0 0. So the only condition that you get is x is equal to 0. So if I have x comma y and the only condition is that x is equal to 0, then you'll get all of these guys, right? Or more generally, whatever independent variable you have, you just keep it as whatever. You can. So in this case, the second variable is independent. Express the first one as a function of the independent variable. In this case, this is forced to be 0, and the second variable is independent variable. So that is why you have 0 comma 1.
You can take it as y equal to t, and you can say 0 comma t. Like we
Yeah.
have learned. Yeah.
So now, just to give you a little bit, our 1 comma 1, if that's the case, can this even be a case? If it was 1 1 0 0 0 0, in that case, you would have x plus y is equal to 0 and no other condition. In that case, let's leave this over here. If the matrix was, say, 1 1 0 0 0 0, then what is the null space of this? The null space of this is x comma minus x as x goes to y. Or you want to be, okay. Why is this? Because even in this case, The second variable is the independent variable. So you let that be t or y or whatever you want. And then the first equation gives you that x plus y is equal to 0. So x can be expressed in terms of the linear, in terms of the independent variable y. X is equal to minus y has to happen. So it has to, all the vectors in the null space are of the form minus y, y. So this is for this, and this is for this.
In this case also,
But
sir, nullity will be 1 only, right?
Sir, it is minus
yes.
y comma y, right, sir?
It's the same, no? It just multiplied by
Same.
Wouldn't that cause any sort of
no,
difference?
minus y comma y and y comma y as y changes in real numbers is the same. If I have 1 comma minus 1, if I do take y to be equal to minus 1 itself, I'll get minus
Okay.
1 component.
No, my doubt is
Rather
then the
than
null
taking y
space.
equal to t, you can take y equal to minus t.
No, 1 comma minus 1 is different than minus 1 comma 1, right, sir?
Yes, but the linear span of 1 comma minus 1 is the same as the linear span of minus 1 comma.
Okay.
Right? So you have 1 comma minus 1 and minus 1 comma 1. So you're not looking at these vectors, you're looking at the span of these vectors, which is just this straight line. Okay, good enough. No. Anyway, you get what I'm saying. Is that fine?
Yes, sir. You can move on.
Yeah. So this is a kernel. So we'll see one more example when I discuss another problem later, where the kernel is non-trivial. Like this is an example, but it was not written explicitly out properly. And in this case, yeah, nullity. Okay. You guys already commented that nullity in these both cases are 1 in this and this. But in our case, the nullity of the matrix was equal to 0, right? Not in this one. In this case, the null space is just the single element set 0, 0. So the kernel is just 0, 0. So the dimension of the kernel is equal to nullity of the matrix. Do you see this?
Yes.
So what is the null space of a matrix or nullity of a matrix? It is the number of independent variables. And whatever number of independent variables you will have that many representatives for the basis of the kernel.
Yes, sir.
Is that okay?
Number of independent variables is equal to
Nullity of the matrix. And nullity of the matrix is the same as the dimension of the kernel because of the correspondence that we have said that kernel of T consists of vectors whose coefficient vectors lie in the null space. So through this example, what the things that we have done using the matrix is that we have associated vectors of the kernel to coefficient vectors of vectors in the null space of the matrix. So in general, if I want to construct a basis, okay, we'll see that in that other example. But this is fine, right? Nullity is the same as dimension of kernel of T. Dimension of kernel of T as a subspace. Because you get that many linearly independent vectors. Now, if I want to see the relationship of image with the matrix, consists of, so image of T consists of vectors whose coefficient vector lies in the column space. Of M of T. So as soon as you're given a matrix, you can do row reduction or row transformations to get two things: nullity and rank. Nullity is the number of independent variables, and rank is obtained by number of pivot variables. And how do you get a basis for the column space? So the null space of the matrix is associated to the kernel. The column space of the matrix is associated to the image. Okay, so let's take this example itself. How many pivots do we have?
2.
Yeah, this and this, right? So the columns corresponding to those vectors,
Okay.
they should form a basis for the image.
Yes.
Yes.
Right? So in the given example, image of T is spanned by, what was it? So it was -362 and
Minus 1.5, 4.5, 2.5.
yeah. Now this is not exactly right, because image T is not spanned by these vectors. Image T is spanned by the vectors
Coefficients.
whose coefficients are these. So to repeat, if you want to find the basis for the kernel, you look at the independent variables and then you take those vectors. How do you construct a basis, or how do you construct a basis for the null space of a matrix? Once you do row reduction, you take the independent variables, and then whatever number you have, you take things like s equal to 0, t is equal to 1, or t is equal to 0, s is equal to 1, you get a basis for the kernel. How do you get a basis for the column space? You look at the columns of the original matrix, which correspond to the pivot columns, and those form a basis for the column space, right? But in this case, you look at those columns and consider them as coefficient vectors, and then you recover the vectors using the basis key. In this case, it -362 and -1.5, 4.5, 2.5, these happen to be these vectors, right? V1 and V2 we had written earlier. It happens to be 1 to 2. So 1 to 2, sorry, P of 1 to 2. This
3 minus 1, 8. Right?
Right, yeah. 3 minus 1, 8. And
3 1 7.
3.
Yeah, 3 1s. That happens to be.
Span.
Since it is injective, this is actually kind of obvious, but yeah, 3 minus 1, 8, 8 and 3 1 7 is a basis for the image. So this is how you get a basis. This, what was it? 317, is it?
Yes, sir.
Is a basis for image of. Okay. Even though I have not given an explicit example for constructing the basis for the kernel, from this point it should be clear how to do it. If in 15 minutes we can cover that problem, we'll do that. But the last thing that I want to cover as far as the concepts go is that we saw that nullity of the matrix is the same as dimension of the kernel. What is the corresponding statement over here? What is the dimension of the image?
Number of elements in the basis of column space.
Two, right?
Yeah, and what is it called? What is the number of linearly independent elements in a column space called?
Rank.
Rank.
Exactly. Yeah. So you know that rank of M of t, this is the last topic, rank of M of t plus nullity of M of t. This is equal to
Number of columns.
Number of columns
number of columns
in the transformation matrix.
of M of t, right? Now, what did I say rank of M of t was? This is the dimension of
Image.
the image plus dimension of the kernel. Nullity is just dimension of the kernel. And what is the number of columns of M of t? So remember what the order of M of t was?
Codomain cross domain.
The number of columns is what?
Domain.
M.
Right? So this is the rank nullity theorem for linear transformations. That the dimension of the image plus the dimension of the kernel always has to equal the dimension of the domain. Okay. So this is rank nullity for matrices, and using the rank nullity for matrices and the correspondence between transformations and matrices that we have seen, we can conclude the rank nullity theorem for transformations. Okay. Irrespective of what transformation I have, the dimension of image of that plus the dimension of the kernel of that has to be equal to the dimension of the domain.
Sir, can you please repeat that last statement again, sir, for the dimension and
No, this is just from here, right? So you agree that rank is dimension of image of P? Nullity
yes,
is...
sir. Yes, sir, but I'm not able to visualize it. So can you just repeat that last statement you made? I think.
Okay, rank nullity theorem for... I just said that rank nullity theorem for matrices you already know.
Yes, sir.
And now we have said that there is a correspondence between matrices and linear transformations. And
Yes,
this
sir.
correspondence is exactly given by rank of the matrix happens to be the dimension of the image, and nullity of the matrix happens to be the dimension of the kernel.
Yes,
So
sir.
the sum of the dimensions of image and kernel does always have to be equal to the dimension of the domain.
Okay, okay.
That's all I said. It was not anything more than that. Okay, so this is the rank nullity theorem, and that concludes the concepts for week 6. Now, in the last 10-13 minutes, let's take some more examples, some problems, try to solve it, or try to see what the ideas are. So, right. Here I have written some problems down. Let's try to solve it. So you have to tell me how to solve it, and I will just... I know how to solve it anyway because I've just written it. So the first question says, asks you to match spaces in column A to isomorphic spaces in column B. So what is the central idea behind this?
So it has to be 1, 1 and on 2.
Sir,
What is...
one is matched to C, I think, because scalar of matrix in R3.
Wait.
It says
Before we try to answer the question itself, when are two, like here we are dealing with the concept of isomorphisms of vector spaces. Now, when are two vector spaces isomorphic? What is the condition?
The transformation has to be both 1, 1 and on 2, sir.
Well, that is the first principles definition. Correct, I agree. But when is the isomorphism possible? There was a statement that I gave in the recap.
When the dimensions are equal.
Exactly. So all we need to know is what spaces in column A have the same dimension. I mean, what corresponding spaces have equal dimension. So all I need to do is compute the dimensions of each of the 6 objects. Well, from an examination point of view, maybe even lesser considering how the question is structured. But let's see. What is the dimension of scalar matrices in R3? So we need to go one by one, right? Let us do one. What is the dimension of
One,
the
sir.
space?
So
One, sir.
can you
For
repeat the question, sir?
What is the dimension of scalar matrices in R3? So now I'll just go 1, 2, 3, A, B, C, and I want the dimension of each of the spaces described, correct? That's how I would solve the problem. So first, let's go to the first entry, that is scalar matrices in R3.
3.
What is the dimension of the set of all scalar matrices in R3?
one, sir.
1, 1.
1.
So the answer is 1. If you want to see why, it will be something of the form lambda 0, 0. Right? So this is just lambda times identity. Irrespective of whether it is an R3 or wherever, it is just lambda I, lambda in R. And this is the span of the identity, if you want to look at it that way. So it's a span of a single element. So this is a dimension 1 space. Right? So what is the second space? This is a subspace of R4 specified by one condition. So what is its dimension?
3.
Yes.
This is 3. If you want, you can verify by constructing an explicit basis. You will get something like, I don't know, 1, 0, 0, minus 1, 0, 1, 0, minus 1. Yeah, I think so. I think it will be something like that. 0, 0, 1, minus 1.
We
All
have
of
to
this
write
will
one
work.
variable as the sum of other variables,
Yeah,
such that only one variable will be dependent and the other would be
So
independent.
you will get this as a basis if you work it out. But in an exam, you would not want to always sit and prove that something is a basis. Just do that substitution and you will readily see that this is a basis. And you should get to that answer too. And what is the dimension of the third space? So what is that third space all about? There's a technical term for it, which we were just discussing a few minutes ago.
So if we can find the rank, it will be 3, sir.
So this space that is described in part 3 is the null space of that matrix, right? So the dimension
Ax equal to 0, yes, correct, sir.
right. So this is how you have to streamline your thought process. First, you understand what the set is. Okay, it is the 0 set of like Ax equal to 0 kind of a thing, x such that Ax equal to 0. So this is the null space of it. So I want the dimension of the null space, which is just nullity. So now I know that nullity plus rank is equal to 3 because this is rank nullity for matrices. And rank I can compute for a square matrix by computing its determinant.
Yes.
What is the determinant of this? The determinant is 0 because that last row is 0, 1, 0, right? You can just expand along the second row and the third row and then you get 0. Or you can actually see that row 1 plus row 3 is equal to row 2. So one row is a linear combination of 2 other rows. All of these things, whichever you can do quickly, you have to see that this is actually a determinant 0 matrix. So it's not a full rank matrix. It's not a rank 3 matrix. But then you can see that it's a rank 2 matrix because column 1 and column 2 are linearly independent.
Yes, yes.
Third will be the dimension of 2.
Yes.
This
One.
dimension is
2. Dimension is 2.
Dimension is 2.
No, dimension is 1.
Nullity is
because,
1.
Dimension
the
is
rank
1.
is. Hey, wait.
So nullity is 1.
Rank is 2. Rank is 2.
Oh, right. Maybe I wanted rank. Yeah, let's see. Okay, this question is. I wanted it to be 2, but let's leave it at that.
Sir,
But the
may I know
point is,
why everyone is telling 2, sir?
We are talking about the rank. Rank is 2. Nullity is 1.
Yes, since we are calculating null space, so we should only calculate nullity only, right?
Yes.
Yeah,
So
yeah.
then dimension is 1.
Okay, yeah, that's what I was arguing. Okay.
Yeah, you can just do the Gaussian, the row reduction of this matrix,
Num-
and then you can see that
number
there's
of
one
independent
independent
variables.
variable. Well, yeah. This is not the right question. I wanted something with 2 over here. I think I messed it up. But anyway, let's do the rest just to do quick dimension computations. What is the dimension of this space?
Two, sir.
Right. So because this will be of the form A, C minus A
Minus C.
minus C. And then there's just A and C which are variable. You can write it as A times 1 minus 1, 0, 0 plus C times 0, 0, 1 minus 1. So you have these two linearly independent vectors, which are matrices in this case, which span the thing, which is a basis. So quickly you can conclude that this is dimension 2. What about the second set?
1, sir.
1.
So this is of the form x comma 2x, right? So this is x times 1 comma 2. Once again, 1 comma 2 is a basis for it. So this is 1. And the column space of this. Yeah, this is the column space of this. So dimension of the column space. What do you want? You want rank.
Yes, sir. 2.
Rank of a, but this is not 2. This is 3. Right?
So is it same as the
No, 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 no.
No,
It's
no,
not.
the last
It's a
entry.
bit different. The last
Okay,
row
sorry,
has
sorry,
2 ones.
sorry.
Sir,
Yeah,
call space is the same as the rank, right?
Column space is a space, as in is a set, and the dimension of the column space is the rank.
Okay.
So this is what? This is 3. This is a full rank matrix. Its determinant is non-zero, or you can just do row operations and conclude this. And you'll get this, but this was supposed to be 2. Suppose this is a correct question where you have some space with 2 as a thing. The correct choice is 1 is mapped to B, 2 is mapped to C, and 3 is mapped to A. In this case, that's not the thing because of an error from my side, but this is how you would solve. And well, the central idea is whenever you're given some question, first you have to analyze what is the concept that is being used. In this case, isomorphic spaces. Isomorphic spaces boils down to computing dimension. And then you just deconstruct from there and then go for it. That was one question. And this second question is
Sir,
quite
sir,
lengthy.
sir. Sir, in the last
Yes.
question, so whenever the dimension will match, only those will be the possibilities for isomorphism.
Yes, and we say that two spaces are isomorphic if there exists an isomorphism between them. And does there exist an isomorphism between them is equivalent to saying, is there a dimension?
Same dimension.
Yeah.
Okay, sir.
In this case, one is mapped to two answers, right? Like first.
Well, this is wrong. So I wanted to give a dimension 2 space over here. I messed
That's
up.
what I think that dimensions would be for the third example. Third is 2.
Yeah, it was supposed to be. I made a mistake.
So in this one would be matched to C, right?
One would be mapped to B. Dimension is equal to
Dimension
1.
has to
Only
be same,
one.
na? 3 to 3, 1 to 1, 2 to 2.
Can you just go up, sir? Scalar matrix is in R3. So, okay. So this one will be mapped to 2U. Okay.
Because both
Sir,
are
I guess
one
he's
dimensional
checking the
spaces.
logic behind 1 and B. That's why he's confused, I guess.
No, I'm not sure what the confusion is. The dimension has to be same, right? One has to be
Yes, sir.
mapped to.
That's the concept, but I think the one
You
who
want an
was asking.
explicit isomorphism, or
No, they are just saying. They are saying like statements of both the thing.
Like he's
okay, let
confused how
me.
scalar matrices are mapped to y equal to
Yeah,
2x.
correct. He's correct. Yeah.
Okay. if you want y scalar matrices, okay, or I'll just write the map between 1 and b is the following.
Okay.
So a scalar matrix is of the form lambda, 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 0,
Right.
0.
Yes.
Yes, right? You will map this to lambda to lambda.
Okay. Okay. Got it. Yeah, I confused myself. Okay. Fine.
Just one parameter is used to
Yeah. It's one
express
dimension only,
both
right?
of the things.
Got
Right?
it.
Yeah. So here y is equal to 2x is just x comma 2x.
Correct.
So this will give you an isomorphism, an explicit isomorphism. But I don't want to do this while I'm solving the problem in the least amount of time. So I have to get to the core concept, which is equality of these, is what I was trying to highlight. Okay, let's try to get this done quickly. There's 7 parts in the exam. You'll not get a question with 7 parts, but I just wanted to cover all the concepts. So let's try to get it done quickly. So the first, so here you have a linear transformation, which is given for, you're only given the value of the linear transformation for 3 values, I mean 3 vectors. And these vectors happen to be linearly independent and hence a basis. And these uniquely determine a linear transformation. This much you can see very clearly. Now, how to obtain an expression for p of x, y, z?
By taking
That's the
alpha,
first
beta,
question.
gamma and solving for them, sir.
Yeah, so this would be p of something times, what was it, 110? No, 101, 110. So
101.
101 plus 110 plus 001. So once again, this has to be y, and in that case, this will be x minus y.
So you're directly solving them, right?
Yeah, I'm just directly solving
Okay.
them. X minus y will have y minus x plus z. You can verify that this is the solution. You will have to, ideally, you have to do something like a0a plus bb0 plus 00c is equal to xyz. But then you'll see that b is equal to y, because the second coordinate, it is like 0 plus b plus 0 is y. So b has to be equal to y. And immediately you'll get a plus b is equal to x. So a is equal to x minus y. And then you'll get a plus c is equal to z. So you'll get the other. You'll solve this. Right? Solve it in
Yes, sir.
whatever way you want,
Understood,
but
sir.
you'll get this. Yeah. So you will get x minus y times 101, which is 1121 minus 12. You will have x minus y times 11 y times 21 z times let's see, y times x plus z times minus 1 2 was it? Minus 1 2. So then you just solve this. It's like x minus y plus 2y x plus y plus oh no. X minus y plus 2y x plus y x plus y x minus z and x minus y plus z is x plus minus y plus 2z. I'm 100% sure that is correct. Let's see. 101 will go to 1 1. Yes. 110 will go to
Sanidhi, please can Sanidhi, please can you mute?
Yes,
what?
sir.
He's sir, bro.
All right. Shall I continue or no?
Sir, it's voice is coming, so that's why.
So this is the expression for the linear transformation. Is that fine?
Yes, sir.
Okay. You have to use the given data and compute this thing. So the next thing says check the injectivity and surjectivity of P. How do we do this quickly? If some vector is mapped to 0, then I'll have 2x minus z is equal to 0 and minus x plus 2y plus 2z is equal to 0. You will have x is equal to z by 2 or z is equal to 2x. Let's just write it as z is equal to 2x. And then you'll have minus x plus 2y plus 2z, which is 4x is equal to 0, or y is equal to 3x by 2. These are all the conditions that you get from for the kernel. So you look at vectors of the
Minus
form
3x by 2, sir.
x, right, 2x. Take for example x is equal to 2. Okay, 2 minus 3, 4. This should be in the kernel. You can quickly verify that this is in the kernel by substituting this formula. 2 times 2 minus 4 is just 0, and then minus 2 minus 6 is minus 8, which plus 8. This is so. This is in P of this is equal to 0. So the kernel is not equal to the singleton set 0, 0. So what is the
This is not
conclusion?
1-to-1.
P is not injective. And for surjectivity, what do we do? You can go about trying to find an image for everything, but you see that the image contains 1, 1 and 2, 1. And the image is a subspace, right? So if 1, 1 and 2, 1 are there, then all possible linear combinations of 1, 1 and 2, 1 are also there. 1, 1 and 2, 1 actually forms a basis for R2. So
on this
the
basis,
map
can we
is,
say all are there?
yes, they are all there. Because the image contains at least 1, 1 and 2, 1, which means the image contains at least the span of 1, 1 and 2, 1, which means that the image contains at least R2. But at least R2, I mean, that is the maximum possible thing anyway. So image is equal to R2. Is this clear?
So this happens just because the images which we had are actually linearly independent. That's why.
Yes, and my target space is two-dimensional, and it has at least two linearly independent vectors. I
Yes.
mean,
So
that is the maximum that can happen.
yes, yes.
So you can actually work out the expression for a general xy, what is the pre-image or what is a pre-image, but that is not the smart way to do it. The smart way to do it is identify that there are at least two linearly independent vectors, which means that the dimension has to be the dimension has to be equal to 2 and the space is the whole thing. That takes care of injectivity and surjectivity. Compute the matrix of T with respect to the standard basis. Now, for standard basis, things are easy, right? What is the matrix of T with respect to standard basis? I'm just going to write beta standard. I'm not going to write beta standard both ways. This is a R3 to R2 map, so it's a 2 cross 3 matrix. And what is the first column? It is, I have to look at this guy T of 1, 0, 0. Second column, I have to look at T of 1, 0, 0, 1, 0. And third column, I have to look at T of 0, 0, 1. Because I'm in the standard basis, right? I have to look at the image of the standard basis vectors and express it in the standard basis on the code. In this case, T of 1, 0, 0 is 2 minus 1. And 0, 1, 0 is 0, 2. and 0, 0, 1 is minus 1, 2.
Sir, sorry to interrupt. Just wanted to ask you a silly question. So, since like we got this transformation like t100 equal to 2 comma minus 1 from the like from the transformation which we found out right before.
Yes, yes.
Okay, so it will be okay. It will be same for any independent vectors, right? Basically, any basis.
You can use any basis, but the advantage with standard basis is that once you write t of 100 is 2 comma minus 1, you don't need to find out what the coordinates of these are, because in the standard basis, this itself will be the coordinates. Here you actually need to write the coordinates, not the vector that you get.
Yes, sir. Yes, sir.
Coordinates, yes.
Yes,
What
correct.
is the coordinates of a vector in the standard basis is just the vector itself.
Okay, okay. Yes, sir. Yes, got it.
So what are the coordinates of x, y? It is x times 1 comma 0 plus y times 0 comma 1. So it's
Yes,
just
sir.
x,
Yes.
y itself
Yes, sir.
in the standard basis. So this is the matrix of the transformation in the standard basis. Now this fourth part asks for compute the matrix of T with respect to this basis on the domain and 1, 1, minus 1, 2 on the codomain.
So in this
And the,
question, we will have to find those coefficients regarding with
you have,
regards to these
yes, you
coefficients.
have to find the coefficients, but
Yes.
notice that what is T of 101 is already given to you. That is 1, 1.
1. Yes.
But what is 1, 1 in this basis?
Okay, it is okay. It is part of the basis.
Yes, it is part of the basis, right? So I'll just write it over here.
Okay, so
So-
the 1 times this and 0 times the other one.
So this will be T of V1, T of V2, T of V3 as the columns. Now what is T of V1? T of V1, it's already given to be 1, comma 1. What are the coordinates of 1, comma 1 in this basis?
1, 0.
It's 1, 0. And T of V2 is 2, comma 1. Let's leave it. Let's leave the second column for later. Let's look at T of V3. That is
0,
T of 0, 0, 1. That is minus 1, comma 2, which is 0, comma 1.
Yes. Sir.
Now we just have to worry about T of V2. Now T of V2 is 2, 1. How do I write 2, 1 as
So
something?
can you explain this one you just wrote like this 1, 0 and 0?
Okay, so T of V1. So this is V1.
Right.
This is V2. This is V3. Now T of V1 is already given in the question. That is 1, comma 1.
Right.
But what I want as the first column is not the vector itself, but the coordinates of that vector. And
Correct.
the coordinates of vector in this basis, 1, 1, minus 1, 2, is just it's 1 times 1, 1 plus 0 times minus 1, 2, right? This vector
Right,
1,
right,
comma
right.
1.
Yes, 1 into 1, 1 plus yes, 0 into minus
So
1.
if you have a vector from the basis itself,
Okay.
then it's like a coordinate vector. It's like 1, comma 0.
And this minus 1, comma 2, okay.
Now, minus 1, comma 2 is the second one, and that happens to be the image of V3. So that will be the third column.
Okay.
Minus 1, comma 2 is also part of the basis. No, that will become 0, comma 1. It is 0 times 1, 1 plus 1 times minus 1, 2.
Minus 1, 2. Okay.
So if you have any vector in the basis, the point is if you have any vector in the basis, it is easy. You don't need to do any computation. It's either 1, 0, 0, 1 or things like that. But what you have to do is work for this guy, 2, comma 1. That is the image of the second vector. Now, how will I express it in terms of this? I need something like
A into the coefficient, right? Again.
Yeah, A minus B is 2 and A plus 2B is...
So A is coming out to be 5 by 3 and B is coming out to be minus 1 by 3.
Oh, is it? Okay, 5 by 3 and minus 1 by 3. Okay, this is a computation that you have to do. A plus 2B is what? A plus 2B is 1. Yeah. If you... Yeah, 3B will be minus 1. So yeah. That's good. So this is the matrix of that transformation. And now these star questions are slightly at a higher level in the sense that it's not exactly derivative from the course content material, you'll have to think a little bit more. So is it possible to have basis beta on the domain and gamma on the codomain such that the matrix of T with respect to beta and gamma has rank 1? Any guesses? It's a true or false, so 50% chance anyway. So this has to do with something that we discussed towards the end. So if the matrix of T has rank 1, what does it mean in terms of dimension of the subspaces that we discussed?
So the image of T will be having rank and so on.
Yeah, dimension of the image of T will
Is
be
1.
is 1. So what you can see is irrespective of what basis I take on the domain and the codomain, the rank of the matrix has to be the same. The matrix might be different. So you see here that with respect to the standard basis, this is the matrix. With respect to this special basis, this is the matrix. You can get different matrices for different bases, but their rank has to be the same because the rank is actually dimension of the image, which is not dependent on the choice of basis. Does that make sense?
So can you please repeat once, sir?
Okay. 4 was done. 5 is, see the rank of M of T. Whatever basis I choose for the domain and what this thing, this is equal to dimension of image of T.
Yes, sir.
Now, image of T is a subspace which is defined irrespective of choice of basis, and the dimension of that is also something that is independent of choice of basis. So this quantity is actually independent of choice of basis.
Okay.
Okay, so it does not matter what basis you choose to represent or choose to write the matrix using, the rank will be the same. The matrices themselves might be different, but the rank will be the same. And you can see that this does not have rank 1, no? This has rank 2.
Yes, sir.
So going back to the question, is it possible to have bases such that the rank is 1? No. Because rank of any matrix, as in you start out with any two bases, the matrix that you obtain as the matrix of the transformation should have rank 2 in this case. In general, the rank is independent of the basis chosen for the representation of the transformation.
So then in that case, then this statement holds, no, sir?
What statement holds?
So when you say that in general that the rank cannot be 1,
If the rank is if the rank is 1, then any matrix representation will have rank 1. If the rank of the if one of the matrix representation is 2, then any matrix representation will have rank 2. In this case, we saw that in the standard basis representation, the rank is 2.
yes.
So any other basis also you use, the matrix representation will have rank 2.
So this is for this particular example, no, sir, which we have solved.
For this particular example, rank 1 is not possible.
Yes, sir. Yes, sir.
Because for any basis, we'll have rank 2 only, right?
Yes, yes. Minimum rank will be 2.
Yeah.
Okay.
Not minimum, exact rank will be 2.
Sorry.
Right.
Rank will
Yeah.
be 2.
Okay, it won't depend on what kind of basis we are having. What vectors we are having.
Yes, the matrices themselves will change, but their rank will not.
Rank
Yes,
will
sir. Yes, sir.
Okay.
Consequently, the nullity will also not. But this is something that you will see in slightly different language in week 7, like similar matrices, equivalent matrices. You'll see this. And the sixth part is also slightly higher level thing. Then what are the possible images of a line through the origin under T? The line through the origin is a one-dimensional subspace of the domain. So under linear transformations, what do you think happens to subspaces? Do you understand this star question?
No, sir.
No, sir.
Okay, let's take a simpler example, not this. Let me break it up. Now look at xy going to x comma 0. So what is happening? What is actually happening?
Reduction in dimension.
So all of these straight lines, they're collapsing to this point, right? So under this transformation, what happens to an arbitrary straight line? What is the image of a straight line through the origin? So suppose I take some straight line through the origin, something like this. What is its image?
It will become x comma 0, something like that.
It will become x-axis only because all of
Obvious.
these will project over here,
Yes.
right? But
Okay.
can you think of a straight line which does not project onto the x-axis?
Y-axis.
Exactly.
Y-axis.
So any line other than the y-axis will project onto the x-axis itself. So image of, I'll call this line L, all right? Image of L is x-axis unless L itself is y-axis. L is the y-axis. And image of y-axis is 0, 0. So this is a special case. But what happens in general is image of a subspace is a subspace. For any linear transformation, image of a subspace is a subspace. But the dimension can go down. So here you see that image of a line is a line. So image of some one-dimensional space turned out to be a one-dimensional space, but there are cases where the dimension got reduced by 1. So the same thing can happen over here. But, well, now I'll have to go into a little bit more. I don't have time to do all of that. But if this was an isomorphism, if there is a one-to-one mapping, then this would not happen. Dimension reduction would not happen. So if you have an isomorphism, then lines go to lines, planes go to planes, all of this happens. We'll not discuss more than that. It is slightly higher level. Now compute basis for kernel and image using matrices obtained in 3 and 4. I will just do the standard basis and I'll leave the non-standard basis matrix representation for you to do. So the standard basis, so this is back to this thing. The sixth question, the answer is line or 0, 0. So in the sixth question, the question was, what is the image of a line? What is the what are the possibilities for the image of a line? It is either a line or 0, 0. Yeah, now how to compute basis. So the matrix representation using the standard basis is 2, 0, minus 1, minus 1, 2, 3. 2, 0, minus 1. What do I do?
Row reduction.
Row reduction to get 1, 0, minus half, 0 to 1.5. I'm happy with this, but let's just do this for completeness. Now what happened over here? What is the, how do I find the kernel? First of all, what is rank? What is the nullity?
Rank is 2, nullity is 1.
Rank is
Yeah,
2,
rank
nullity
is
is
2, nullity is 1. So dimension of the kernel is
1.
1.
and dimension of the image is 2.
Yes.
So how do I find a basis?
So sorry to ask, what was dimension of the image?
Dimension of the image is rank of the matrix.
Is rank of the matrix. Okay.
And dimension of the kernel is nullity of the matrix. Okay.
Dimension of
So,
kernel is nullity of the matrix, and okay, I got it.
okay. So how do I find a vector in the kernel? What is the
So
independent variable?
independent variable is x3.
Yeah.
We can say x1 plus minus half times x3 is equal to 0. So x1 is equal to t by 2 minus t by 2.
Is it
Sorry,
this
t
much
by
p
2.
by 2?
Yes, yes, sorry.
Yeah. And then you have 4x1. Or yeah, let's just keep it in terms of t. This is negative 3t by 4.
So last one would be x2, no?
X2, sir. X2 is minus 3
Oh,
t
yeah.
by 2.
Yeah. You have something like 3 by 2 minus 3t by 4 and t.
Yes.
So similarly, you can do for using these two columns, you can find the basis for the image. Okay, so this is actually the kernel because this is actually coordinates of the kernel vectors. But in this case, coordinates is the same as the vectors because we are in the standard basis.
Yes, sir, yes.
Okay, so let us just do using the other matrix also. Let's try to compute the basis for the kernel because I want to show how using coordinates also works. So what was the matrix? 1 5 by 3 0. This is almost there, right? So we don't need to do much work. 1 5 by 3 0 0 minus 1 by 3 1. 5 by 3 minus 1 by 3. So this is in terms of the special basis. So we have a 1 0 5 by 3 minus 1 by 3 0. So in this case, you already have a 1 multiplied by minus 3 and you'll get this 0 9 minus 3. This is sufficient. We can just do this. But then I have to do some. I'll just leave it. I can do that.
Yes, sir, can't
Is
we
this
have
correct?
the first column and third column as independent? Sorry, dependent.
Well, you'll get the same answer
Okay,
because
sir.
you will have nullity 1. You can check that also. But wait, I'll ask my thought. This is 5 times, so this is minus 5. I believe so. Yeah. No, add it. So it's plus 5. Sorry. Now this is also, as expected, rank 2 nullity 1 matrix. But in this case, what would a element of the kernel look like?
Minus 5t plus 3t.
T.
But note that these are the coordinates, or it is the span of 531. Let me just call it the span of 531. Kernel is the span of 531. But it's not actually 531, but it is the vector whose coordinates are 531, minus 531. What is the vector whose coordinates are minus 531? The basis was 101, 110, and 001, if I remember correctly.
Okay.
Right? 101, 110, 001. Is that the something that I've written? 101, 110, 001. Yeah. So what is the answer for this? -2, 3,
-4.
-4. So it's like the kernel is actually 2t minus 3t, 4t. I've just multiplied by a negative sign and taken the span. And you see that that is the same as this, right? If you multiply this by, say, 4, you'll get 2t minus 3t and 4t. So you will definitely get the same answer for the kernel, but the extra step is that when you solve using the row reduction, what you get is the coordinates. You have to recover the vector by using the basis to get the standard coordinates of the vector. So kernel of t is actually equal to this. Is that clear?
Sir,
Yes.
sir, I thought, -5, 3, and 1 should be equal to A times 101, B times 110, and C times 001, and the corresponding value of A, B, and C would be that. I thought that, maybe I'm not
No.
sure.
You should not. No. So the matrix, whatever thing is associated to the matrix,
Hmm.
that is the coordinate vector.
Yes,
So
sir.
-5, 3, 1 is the coordinate vector of the vector in your domain. You're not finding the coordinates of -5, 3, 1. You will find the coordinates of something associated to the vector space, and something associated to the matrix is already in the coordinate form.
Okay.
So
So
this is in the coordinate form.
-531 are the coordinates.
Are the coordinates, yeah. Values associated to the matrix representation are the coordinates. Is that clear?
Oh, yes, sir.
So I should, strictly speaking, I should not say span of that. 531 is the coordinate vector.
Yeah, actually, so when you're using span, so that's why I
Yeah.
was getting a bit confused actually.
So 531 is actually something like V, whatever that thing is, beta.
So you'll be
And
sharing this note, right? Okay.
sorry?
You'll be sharing the note, right?
Yeah. I put it in the same folder.
Sir, both question and today's notes, sir.
Yeah, everything will always be shared.
Okay, sir.
Yeah. Okay, and it's already 10:30. We'll wrap up unless you have any doubts.
So sixth week is over, like or?
Yes. Content of 6 week is done.
Sir, is there any way the dates will get extended?
Yes, sir. Actually.